I'm going to introduce you to a new distribution. This distribution is called the t-distribution. The t-distribution is bell-shaped and symmetric. The center is at 0, which you can see right here, mu equals 0. And the spread is controlled by what we call the degrees of freedom. The way you find your degrees of freedom is to locate how many people you sampled, your sample size, and then subtract 1. So sample size minus 1 is your degrees of freedom. When the t-distribution has a small degree of freedom, basically a sample size smaller than 30, you get a shape that looks like this. When your t-distribution has a sample size that's close to 30, you'll get a shape that looks like this. If you notice, I've compared these to what we call the z-distribution. So the t-distribution has fatter tails than the z-distribution. The other thing that you'll notice is that the t-distribution has a lower peak than the z-distribution. What we're saying is that this height on your t-distributions is farther down than the height on the z. The main point of the t-distribution is to allow greater variation in responses. You're saying there's a bigger chance that people may give an answer on the extreme, and there's less of a chance that everyone's going to give this exact same answer in the middle centered around mu. The last thing to point out is that every time your degree of freedom changes, you'll get a different shape. So this may be a degree of freedom 1, degree of freedom 2, degree of freedom 3, degree of freedom 4, 5, and then eventually, as your sample size increases enough, as your degrees of freedom approach infinity, what will happen is this t-distribution will become so close to the z-distribution you can't really tell a difference. A lot of times, instead of using the number infinity, people will use the number 30 as that cutoff value, saying, okay, you can switch from the t curve to the z curve. Let's look at some of the theory that separates the z-distribution from the t-distribution. Let us say you take a simple random sample from the sampling distribution of the sample mean, which says that x bar is normally distributed with mean mu and standard error sigma over the square root of n. The z-score would come by subtracting mu and dividing by sigma over root n. Subtract mu, divide by sigma over root n. When you use sigma in this problem statement, that ensures that you are on the standard normal curve. So if sigma is known, you're on the z distribution. However, in real life, most of the time you won't know sigma. So now let's say you take a simple random sample from the sampling distribution of the sample mean. But this time when you divide by the sample standard deviation s. When you use s, that makes you fall on the t-distribution, which is controlled by the degrees of freedom. Now both of these values, and let me show you, when I say these values, I'm referring to the z-score or the t-value. Both of these values basically count how many tick marks you are from the population mean. If this is where you're centered, they're basically counting how many tick marks did you fall above or how many tick marks did you fall below this population mean. By the law of large numbers, as n increases, the statistic s approaches the parameter sigma. So what we're saying is that if n is large enough, this value of s will become infinitely close to the value of sigma, which therefore means that the t becomes infinitely close to the z, which therefore means that the t curve right here basically becomes infinitely close to the z curve right here. Once n is large enough, you can't tell the difference between the t and the z. They take on the same shape. Now, saying as the sample size increases isn't very specific. How much does it have to increase by? Well, generally the rule is once the sample size increases to the number 30, you can switch from the t-distribution to the z-distribution. On here, we're saying that once n is close to 30, the t-distribution and the z-distribution will basically look like the same curve. They'll give back the same probabilities just about. Let's practice working with the t-table. Our notation for this says t sub alpha of n minus 1. Alpha will be the area under the t-curve to the right of the t-value. So for example, find the t-value with right tail area, 0.05, and degree of freedom, sample size -1, 13. This means we asked 14 people, but the degree of freedom is 13. Notationally, I'm finding t sub 0.05 of 13. And this number will be the number that has 5% above it and 95%, 0.95, below. Now when we looked things up on the z-table, we had to look from a number and down. But on the t-table, you're going to look from a number and up. Here's a section of the t-table. See in the picture, it tells you you need to look for right tail areas. So if I line up my degree of freedom 13 with my right tail area 0.05, that gives a t-value of 1.771. Now what if I wanted you to find the tail area to the left of a t-value? So in this example, I want us to find the t-value with left tail area 0.001, and we know the sample size is 40. Your degree of freedom is the sample size -1. So in this case, we have 39 degrees of freedom. Now we know that the table is going to give us a right tail area, but the idea here is that we should use the property of symmetry. By symmetry, the t sub alpha of n-1 of your degrees of freedom is positive on the upper end. So if we want to find the lower end t-value, we'll just change the sign. I'm basically saying put a negative in front of that t-value that you look up. Let's go to the table. Here I have found 39 degrees of freedom with an alpha of 0.001, and the t-score that goes with this is 3.313. So we know the upper end t-value is positive 3.313. which means that the t-value we're looking for will be negative 3.313. And this is the t-value with left tail area 0.001. In the last case, I want you to find a t-value that corresponds to 95% confidence with a sample size of 11. When you see the word confidence, what you need to picture is 95% in the central area. What I'm building up to is how to create confidence intervals. So it's going to say something like form the 95% confidence interval or 90% confidence interval. So confidence means the center area is that number. Now the idea here is that if there's 95% in the middle, then on your tails that leaves over a total, if you were to sum them up, of 5%. That's your tail area on both ends. That's your alpha. Now, for us to look this up in the t-table, what we're actually going to have to do is look at just the tail area on one end. You could look either on the lower end or the upper end. And since we know the t-table gives the area from a point and to the right, it'd probably be smarter for us to look up the upper end, the right tail area. So we'll take this and divide by 2. So if you take alpha and divide by 2, that leaves over 0.025 on the upper end and 0.025 on the lower end. So that's where this alpha over 2 comes from in the formula. The other thing that we need to recognize is that the t-value on the upper end will be positive, and the t on the lower end will be negative. But both of them have tail area 0.025. And then the last thing that we need is to know the degrees of freedom, n-1. It says we sampled 11 people, so our degree of freedom is 11 minus 1, 10. Let's go look this up in the table. I've taken my alpha value of 0.05 and divided it by 2. That's 0.025. So now in the t-table I'm looking for 0.025 with 10 degrees of freedom. That's 2.228. So we now see that there's two t-values that we can find to control this 95% in the middle. There's your lower end t-value and your upper end t-value. When you're creating a confidence interval, you always want to use the positive t-value. So here, our final answer will be positive 2.228. Here's another example. Find the t-value that corresponds to 95% confidence with a sample size of 1,000. Let's try working it from the formula without using the picture this time. When I see 95% confidence, that makes me think of an alpha equal to 0.05. So I know that my t-value should be t sub alpha over 2 of n minus 1. That's t 0.05 divided by 2 of my sample size minus 1. That's t 0.025 of 999. Let's go find this in the table. So here's 0.025, but when I look for the number 999, it's not on the table. However, 1,000 is. So what we'll have to do is go very close to 999. We'll have to just use the 1,000, and that's 1.962. So here we'll say our t-value is approximately 1.962. Now what if we change our sample size? What if we bump it from 1,000 up to 2,000? So again, t alpha 0.05 divided by 2 of n minus 1. That's t 0.025 of 1,999. When you look in the table for 1,999 with tail area 0.025, you're not going to find a number that large. Do you see that they give you the z? What they're saying is that your degree of freedom, you're on the t-distribution all the way up to about 90. Once you hit 100 and 1,000, you're pretty much almost on the z, and by the time you hit numbers bigger than 1,000, you're on the z distribution. So here, we'll say that's 1.96. Let's take a look on the table. Here's 0.025, or 95% confidence. When your degree of freedom is small, 1, you're at 12.7. As your degrees of freedom increase, your z-score decreases. If you're at a degree of freedom 90, your z-score drops down to 1.987. Then when your degree of freedom goes to 100, it drops again. You're now at 1.984, and then when your degree of freedom hits 1,000, you're at the 1.962. And by the time you hit bigger than 1,000, you're on the z distribution. Now here's the second way that you can use the table. Let's say that we have a population of size n equal 25, which, remember, knowing that n is 25 means your degree of freedom, n minus 1, is 24. So we have this population of size 25 taken from a population that's known to be normally distributed. The first thing I want to know is what right-tail probability corresponds to t-value of 2.008. So here I've drawn a picture to represent the situation. I've labeled our t-value 2.008 and our degree of freedom 24. I'm basically saying a t-distribution has what right-tail probability when the degree of freedom is 24 and the t-value is 2.008. Let's go look at our table. Here's the degree of freedom 24 column. And now I'm going to scan through for my number 2.008. But it doesn't fall exactly on one of the numbers they gave us. It falls between the two numbers. And the two numbers it falls between, 1.711 and 2.064, correspond to tail areas of 0.05 and 0.025. What we're saying is that the probability that we're looking for, the one in black, is somewhere between the values 0.025 and 0.05. So we can say that the probability value is somewhere between 0.025 and 0.05, or the p-value is somewhere between 0.025 and 0.05. Here's another one. What left tail probability corresponds to a t-value of negative 1.421? So in this one, I'm trying to figure out the probability of being less than negative 1.421 equals what? Remember, you could think of this as negative t sub alpha of n minus 1, or of your degrees of freedom. And you know that this number is equal to negative 1.421. We must remember that the table won't tell us the value from a number and down. It will only tell us the probability from a number and up, so we'll need to use our symmetry property. So we'll have to remember that whatever this probability is, it's the same probability as being at positive 1.421 and larger, the positive t sub alpha of 24. Let's go look in the table. Here's my row with 24 degrees of freedom, and I'm looking for the t-value 1.421. This is trapped between probability values of 0.1 and 0.05. So in the picture, I'm trying to show you that the probability you're looking for is somewhere between the number 0.05 and 0.1. And by symmetry, we know that this value for the upper tail is the same as the probability for the lower tail. So in our answer, I'll just give bounds on this probability. I know that the probability value is bounded somewhere between 0.05 and 0.1. It's very important in reading the words that you pay attention to whether you're talking about looking for a probability on one tail or two tails. Here in this one, I'm asking what two-tailed probability corresponds to both of these t-values. I'm now trying to figure out what's the probability of being less than the lower tail plus what's the probability of being greater than the upper tail. I want to find the probability on both ends. Oh, and the other thing to remember is that your sample size was 25, so your degrees of freedom are 24. Let's go look in the table. Here's the 24 degrees of freedom, and my t-value was 2.797. So on this one we got lucky. We see that that lines up exactly with a probability of 0.005. So I know the upper tail is 0.005, which automatically means that the lower tail is also 0.005. So to get my final answer for the probability value, or the p-value, all I'm going to do is add the probability for the lower tail, 0.005, plus the probability for the upper tail, 0.005. And when I add these up, that gives me a probability value, or a p-value, of 0.01. These are all the ways that we're going to be using the t-table to find values.